Well, hello. Today we're going to be looking at the rectangular coordinate system, sometimes called the Cartesian plane or coordinate grid. Um, Whatever you want to call it, we're going to be doing some graphing. So this is the things that we're going to mainly hit today. We're going to be looking at plotting points, graphing some lines. This is ultimately like an application. We can see here that what we have is Lamar recorded the weights of the sun's height and weight. And generally speaking, you might think of this as height increases, weight also might increase. It kind of makes sense. You can see here that this is listed as the height is the x and the weight is the y. And over here we have a grid, and you can see as well that we have this is an x-axis, and then this is our y-axis. And what we will be doing is using these numbers to plot them on a graph so we can get a picture and make sense of our data. Now, because we already kind of suspect that as height increases, weight will increase, right? As height goes up, probably the weight will also go up. And so we think that as one increases, the other increases, our graph might look something like this. We don't know yet because we don't know exactly what all these numbers mean, but that's just a little bit of a guess. Okay, let's go ahead and do a little bit of warm up and kind of remind ourselves about some number lines first. Well, when we graph a number line, this says from 0 through 10. So I'm going to start out just by making a line. And whenever I want to make a number line, a lot of times what I'll do is I'll kind of put where I want to start, I'll put that first, and I might call that 0. And then I'll put where I want to end up with, and maybe make that like 10. So something like that. Then what I'll do is I'll go about halfway in between, and we'll call that about 5. So what this allows me to do now is it's kind of hard to put in equally spaced lines from 0 to 10 sometimes, but I can go 0 to 5. That just makes this a little bit easier to say 1, 2, 3, 4, and they're somewhat equally spaced. 5, 6, 7, 8, 9, 10. Not great, but not too bad. From there, then, it does say to label number 7. So right here's 5, 6, 7. That's this point right here will be our number 7 on the number line. For the next one, it says to number the lines from -5 through 10. Well, when I do this, I already kind of know, I already have 0 to 10, and I could just copy and paste that down here. But here's what I'm going to do is I'm going to put 0 on about right here, call that 0. I'll come over here and I'll put 10. And now I remember that -5 is going to be to the left. So if about right in here is going to be +5, because that's kind of halfway between those, I'm going to go this same distance, however far this is, I'm going to go that far over to the left, about that same distance. So we'll go about that far and then call this -5. Now I have a nice number line from -5 up through 10. If you'd like to put all of the little tick marks on in between here, you absolutely can. We have 0, and then we have 1, 2, 3, 4. Here's 5, 6, 7, 8, 9. I didn't do the best job there. 10. And if we want to go the other way, this will be -1, -2. Oops. Let's see. Let's try that again. There we go, -3, -4, and -5. Sometimes I like to make those bigger ones, or those like 5s and 10s, I'll make them a little bigger to see it easier. Label 3 on the number line. Well, +3 is going to be to the right of 0. It's between 0 and 5. So right here is the number 3. By the way, -3 would be over here if it said to do that. Remember, the negatives are to the left. Okay. Next, it says construct a number line from -100 through 100. Well, don't get too concerned about this. We're not actually going to put all those tick marks on there. We only need to put just a few marks on here to kind of give us a sense of direction and scale. So I'll come over here and I'll call that 100, and I'll go about the same distance in the other direction, call that -100. I'm not going to put all these in. You could put 10s if you wanted. Go 0, 10, 20, 30, 40, 50, 60. I don't even think I'm going to do that for this one. So it says label -33. I'll put, something on here. I'll go about halfway and call that 50. And this will be -50. And now -33 is going to be somewhere between -50 and 0. Now remember, about right here would be -25. but that's not quite far enough. So I'm going to go just a little bit past that, maybe a little bit closer to the negative 50 than I would closer to the 0. Because negative 33 is closer to negative 50, so it's a little bit more than halfway. That's probably pretty good for what we're doing there. Next, we're going to graph these numbers, and I know a lot of people see these fractions, and you're like, oh man, no way, I'm done. Fractions, no thanks. But let's just look, notice they're all eighths, and that does make this kind of nice because they're all eighths. Let's just kind of ignore that for now, and we'll look at the 7 through 11. So again, I'll start out with 0, and then I'll have negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7. So this will be negative 7, and then I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then 11, we'll call that right there. Sorry, that's a little close. Now, again, you might be thinking like, wait a minute, I thought that we were going 7/8, negative 7/8 to 11/8. Well, the nice part about this is I can actually divide every one of these numbers by 8. And now I have a lovely number line from negative 7/8 all the way up to 11/8. And now it says label 3/8 on your number line. So 0, here's 1/8, 2/8, 3/8. Right here is 3/8. Okay. Now, an XY ordered pair gives us a left and right part. That's going to be the x's. This is going to tell us left and right. And then the y is going to tell us the up and down. Remember, because the horizontal axis is always going to be, pretty much, always going to be the x-axis, and then the vertical part is always going to be the y-axis. Okay, y's are the rise. So when they give us an ordered pair, the first number will be left and right, the second number will be up and down. Right? Positive numbers to the right or up, and negative numbers will be to the left or down. So looking at these numbers here, I can see my first one is this right here. This is A, so I can, if I want to talk about this, is going to be left 2 and then down. And so that'll make this ordered pair negative 2, negative 2, because it's left 2 and then down 2. Now for the next point, which is our point B right here, this is going to be left and right 0. We always come back here to this origin right there. That origin, as it's called, that's 0, 0. Everything is going to be in relation to that. So I can see that this one is up 3, but it's not, it's left and right none. I don't have to move left and right any, so it would be 0, 3, because it's left and right 0, but up 3 from the origin. For part C, I can see this one over here. I'm going to have to go left 1, 2, 3, 4, and then up 1, 2. So this is the ordered pair, negative 4, positive 2. And then lastly, for letter D, which is kind of hiding over here, it's hard to tell, it's right on top of this one, I can see that this is over 4, so it's to the right 4, and then it's going to be down 1. And remember, when we go down, that's a negative. So my ordered pair is the ordered pair 4, negative 1. So remember, the first number is always the left and right. The second number is always the up and down. Positive numbers are to the right or up, and negative numbers are down or to the left. Next, let's take and plot a few points ourselves. When we look at this graph that I have here, I notice there's a lot of these little in-between lines. There's some bigger lines here. Here's 0, 0, and here's over 2, but I actually have several lines in between here. So that just means you got to pay close attention to that. This graph is scaled a little bit differently. See, right here would actually be 1, and then that means that we have these spaces in between here. Each one of these is a half. So our graph is scaled a little differently. Make sure to make note of that. We have 0, 4. Remember, this is the x value or the up and down, or sorry, the left and right. So we're going left and right 0, but we are going to go up 4 because that's a positive 4. So I go left, right 0, up 4. Right here is number 4. So that's this point right here. This is the point 0, 4. The next one is negative 2, 0. So this is the x value, so that's left 2. So I'll go over here to negative 2, and then it's up 0. So this is the ordered pair, -2, 0. The next one we have is 1, 5, so that's over 1. Remember, I already put 1 on here because this is 2 and 1 is halfway in between. And then I'll go up 5. But again, it's kind of hard to tell. Remember, here's 6 and here's 4, which means 5 would be right in here. So I'm going to go 1 and then 5. That's this corner right there. That would be the ordered pair over 1, up 5. Our last one then is 4, -4. So that's to the right 4 and then down 4. That would be this little intersection right here. So +4 to the right and then down 4 because it says it's a negative. These are all pretty nice numbers. Let's go ahead and take a look at some on the next screen that aren't quite as nice. Here we have some fractions. Now, I could try to graph 3/10. Notice I don't have any numbers on my axes anymore, so I can scale these however I want, which means I could make each one of these blocks. I could make this block right here, I could make this a unit of 1. I could make it a unit of 2. I could make it a unit of 100. But if I did that, these are all really small numbers. They would all, I wouldn't really be able to tell much. But I could also make each one of these blocks to be very small. I could make this to be a half, or I could make it be 1/10 or 1/100th. And so I think what I'm going to do, because when I look up here, I see this is 3/10, 21/10, fifths, which I know could be tenths. You know, I think I could make them all tenths. The only one that really makes this one kind of hard is this guy right here. So while there's not one great way to do this by hand, we're just going to get as close as we can. I see my largest, if I want to put all these on the same graph, and that's what I'm going to do here, I know I need to be able to fit a 2 on here. So I can't just go by 1/10 each time. If I did, I would have to get this out to 20/10, and I don't have 20 numbers here to be able to do that. So here's what I'll do is I'm going to come over here, I'm just going to call this 1, and I'll call this one right here, I'll call that 2. And we're going to approximate these the best we can. So I'm just going to do this, call this 1 and 2, and then -1 and -2. If you'd prefer for decimals, you can change these into decimals easy enough. That's 0.3. 21 divided by 10 is 2.1. So, you know, 0.3 and 2.1, that would be over 0.3. So right here would be 0.5, so it's got to be less than that. So about here. And then up 2.1. So here's 2, and we'll just go a little bit more. So this would be the ordered pair, 3/10, comma, 21/10. Is this exactly the best way? Well, I don't know. Best is a little subjective. This does get us right about where it is, though. Let's keep going. -3/5. Well, if you want to, you can change that into a decimal, if you'd prefer decimals. -3/5 is a little more than half. So that would be, here's half, so it'd be a little bit past it. And then down 1/10, so down just a smidgen. So right in there, this would be -3/5 and then -1/10. Should maybe write a little bit nicer. Put a parenthesis. That looked a lot like a 1. All right. How about a half and -1? That's a lot easier. Over a half, because it's halfway from 0 to 1. So half and then down 1. So that would be right here. This is our ordered pair, 1/2, -1. And the last one, 2/7. So one more time, we're going to go over 2 and then up 7/10. That's a little bit less than 1. And so that would be about right in here. So this would be the ordered pair, 2/7. Now, we could have also scaled this graph and made each one of these like 1/5. That would actually turn out pretty nice. But, you know, we're pretty good like this. If you want to scale all these down to 1/5, you could. And then some of these would also still be in between where we were at now. Another thing I see some people do sometimes is if they scale this all to 1/10, when they go to graph something like 21/10, they end up just coming way off the graph over here, and You know, I get it. At least you're putting it in the right location. But work with what you have and rescale it to make it appropriate for what you're doing. For example, on this one, I can see that I need to get to 1,000. My biggest number is 1,000, so I have to be able to fit 1,000 on here. So I think this time what I'll do is I'll make each one of these lines, even these smaller lines, I'll make each one of these to be 100. So I have 100, 200, 300, 400, 500, 600, 700, 800, 900, 1,000, right? So I'll do something like this, and this is just going to scale my graph. Again, we have 1, 2, 3, 4, 500 would be here, and then 6, 7, 8, 9, 10, or 1,000 would be there. And I know that these don't line up on these darker lines, but that's okay. We're scaling the graph to make it for what we need. So 1,000, that's in the X direction or the left and right. So we're going to go to right 1,000 and then up 450. That's our Y value. So here's 500. So we'll go right between 400 and 500, and that would be the point 1,450. The next one, negative 200, negative 700. So I'll go back to 1, 2. That's here, and then down 7. 1, 2, 3, 4, 5, 6, 7. So that takes me to right here. This would be the ordered pair, negative 200, negative 700. The next one, negative 650, 500. So that's back 6. 1, 2, 3, 4, 5, 6. Here's back 6. Here's back 7. I would go right in between those two, right? So right in here would be negative 650, and then up 5. So if you count those out, should put us to right there. So 1, 2, 3, 4, 5, 6, 650, and then up 1, 2, 3, 4, 5. That's 500. Our last one is 400 and 0. That's to the right 400, and then up 0. So that's just 1, 2, 3, 4. Remember, each one of these is a value of 100. So there's 400, comma 0. All right. So scale your axes however is appropriate. We can also have x and y be related to each other. We can do this in a linear equation. This is the standard form of a linear equation. It's ax plus by equals c. Here's an example of what that might look like, because I know sometimes variables can be a little confusing. This just might say like 2x equals 2y plus 5. Now remember, this is 2 times x equals 2 times y plus 5. A solution to this would be ordered pairs that work for this, or ordered pairs that balance the equation when you substitute them in. For example, maybe I might think that the ordered pair 2, 0 is a solution. Maybe. I could check that. If I put this in for the x and I put this in for the y, does it work out? Well, if I put 2 in for x, I would have 2 times the 2 that I'm putting in for x, and then 2 times the 0 that I'm putting in for y, and what I would find is 4 equals 0 plus 5. 4 equals 5. Well, that means that this is not true. That is not a solution. It doesn't work. That's because it does not balance the equation. There's only certain numbers that we can put in here and cause the equation to balance. I have over here a table, and we're going to try plugging negative 7 in for x and figuring out what y. So if I take the negative 7 and put it in place of this x right here, so 2, and I'll put the negative 7 right there, equals 2 times y plus 5. Well, multiplying this out, this is negative 14 equals 2y plus 5. We know we always want to balance our equations, so I'm going to try to isolate this y, and I'll subtract a 5 from both sides. And this gets me negative 19 equals 2y. And then I can divide both sides by 2 and find out that y is equal to negative 19 halves. Now, that might not be the best number. You might not like that as much, but if you actually go through and divide that out, 2 goes into 19 9 times with a remainder of 1. So 9 and 1/2, oops, there we go, 9 and 1/2, or 9.5. That means that Negative 7, comma 9.5 is a solution to this because when we substitute negative 7 in for x and we substitute 9.5 in for, oops, hold on, that's a negative. Whoop, there we go. Almost forgot. Well, I did forget for a second, but I caught it. All right, because I started working this through in my head and I thought, wait a minute, there's no way that if I put a negative 7 in here, I get negative 14. If I put a positive number in for y, I'm going to get a positive number back out. Right, so I knew that my answer, if I had a positive 9.5, just wouldn't make sense, and that's why I kind of caught that. So always go through and check your work here. All right, so this is a solution because it works. When we put negative 9.5 in for the y, right, we'll get negative 14 back out as the final answer, which that's what the left side would be. Let's try it with this one. Notice this time in the other part of the table, so this time we'll take the 7/2 and put it in for y. And again, I know some people don't like fractions. If you want to change that to 3.5 or 3.5, you can. But this is a nice easy one. 2 times 7/2, 2 times 7 is 14, divided by 2 is 7. So the right side of this is 7 plus 5 equals 2 times, and we don't know this x, so I'm going to leave this as x, right? So 2x. This then is just 2x equals 12. We'll divide both sides by 2 to try to isolate that x, and we do get x is equal to 6. So x equals 6 when y equals 7/2. That would be the ordered pair that relates to each other. For this last one down here, notice we have the x is 8, so I'll put 8 in for the x, and we don't know the y value. That's what we're going to try to find, so I'll leave that as y. On the left-hand side, I get 16 equals 2y plus 5. I'll subtract a 5 on both sides, and then that will get me 11 equals 2y. When we divide, that gets us our y value of 5.5, or 11/2. I actually prefer to leave numbers as improper fractions myself, so 11/2. If you want to, you can divide that out, though, and get 5.5. We can always verify that by plugging these back in. So 8 and 11/2, if I put them back into my original equation, 2 times 8 equals 2 times 11/2 plus 5. On the left-hand side, this will become 16, and on the right-hand side, 2 times 11/2 is 22/2, or 22. Oh my goodness, I did it again, didn't I? Look at this. It doesn't work out. It doesn't work out. That's because I did my multiplication wrong in the check. 2 times 11/2 is 22/2, which is 11. There we go. 16 equals 16, and that does work out. Okay, good. We did do it right. We almost got it wrong because I checked it wrong. All right, let's keep going, though, and look at a few more. So you'll notice this time we don't have an equation written in standard form. X, y, and z. Just like on the last one, we had x's on one side and y's on the other. But the nice part about this one is this is actually y equals. And you'll find this a lot in math. This has a different name for it. It's so common, it's called slope-intercept. We'll look at why that is a little later. But the nice part about this is when we go to substitute these numbers in for x, it already has the y isolated. Right, so this is y equals, and then 6, we'll just put our number in right here and then add 5 to it. So when I put -2 in, put that in right here, I get 6 times -2 is -12, plus 5 comes out to be -7. So that means y equals -7 when x is -2. We'll do the next one by plugging a 0 in for x. I always like doing those because plugging zeros in make things really easy. 6 times 0 is 0, and then plus 5. So our y value is 5. Y equals 5 when x equals 0. The last one's when we plug a 2 in for the x. So I'll come up here and I'll put 2 in for the x. And this gets me 6 times 2 is 12. 12 plus 5 is 17. So when when x equals 2, y equals 17. Now our directions here say complete the table. Okay, good, did that. Choose two ordered pairs to graph the equation. Now, I could choose this one, but you know what? That number's kind of big, and I would have to rescale my graph. I'm going to choose to graph these other two ordered pairs. I'm going to graph this one here, and I'll graph this one there. That's because both of these are relatively small numbers, and they're easy to graph. I don't have to rescale my graph at all in order to do that. So -2, -7 would be to the left 2, and then down 7. So 1, 2, 3, 4, 5, 6, 7. Whoops. Calibration's a little off. 0, 5 would be left and right 0 and up 5. That would be to right here. Now, the thing about this is, oh, by the way, 217 would be here and then way up here somewhere off my graph, right? But in actuality, there's a lot more x and y's that will work for this. I just chose a couple x values and plotted them, but this right here just says that any y value is always going to be 6 times as large as x and then plus 5, or 5 more than 6 times as large as x. Whether x is 0, if x is 1, if x is 2, if x is 3 million, it doesn't matter. X could be anything, and y will always be 6 times larger than that, plus 5. So we actually represent that in math using a line. And what this line shows me is that it's a representation of every single x value and its corresponding y value. There's infinitely many of them. I could graph one at -0.1, and then it would be the y value would be like right here. I could graph one at +1, and then the y value would be right up in here. Okay, and you can see this line right here would actually go up through about where that point is. We like to put little arrows on the ends of our lines to kind of say that, like, hey, this line is going to keep going on forever and ever and ever in that same direction. There's a nice graphing program that's really fun to play around with. It's just called Desmos, D-E-S-M-O-S. It's totally and completely free. You do not have to make an account. And if we come in here and I just typed in y equals 6x plus 5, and I can graph it, and yeah, this looks a lot like that line that we just made. Kind of has the same steepness, it kind of has the same direction. The nice part about Desmos is I can actually zoom out and I can see this line's going to keep going. Notice it just rescaled the graph for me, but I can go all the way out. Look, it's going to keep going on forever. I can zoom all the way out, and this line keeps going. Look, over here is 5,000 now. So that's a really nice part about Desmos is it will rescale for you. It kind of shows you what this graph should look like. And we can even find some of these points that are on here. I know this was the 0.05, and if I come over here and I can click right there and just find, oh yeah, it does have the 0.05. Or I can look down over here and find this one that we had, which was -2, -7. That was another point on our graph. But this line represents all the points. You can see that as I change with my x values, the y values also change. Okay? I would definitely encourage you to get on and play around with Desmos a little bit because it will help you with your graphs. In fact, when we have something like this, sometimes it's nice to get an idea of what this is going to look like even before we graph, just so we know that if we're doing it, maybe are we doing it right. So let me pull up Desmos again, and I'll type this in as just 1 divided by 4. So 1 divided by 4, and go over x. So 1/4 x. Okay, I'll hit the little home button, it resets my graph. I can see it's still going to have this nice line that goes through here. But this time it's not quite as steep. The other one seemed to be going up a lot, and this one seems to be going over more than it's going up. We'll explore that a little bit later, but let's just kind of keep that in mind so that when we go to graph this, our line should also kind of have the same attributes in that it's going over more than it's going up. So let's work on taking this and plugging this in. So we'll get y equals 1/4, and I'll substitute a -1 in. That makes this real easy. That's just -1/4. And when I put a 0 in for x, I'm going to get 0 back out. And if I put a 1 in for x, I should get 1/4 back out. Now, one of the things that we're practicing on this page, again, is this idea of rescaling a graph. So if we rescale it, it will make this a little bit easier. If I try to plot just -1/4, like -1, -1/4, that would be somewhere down in here. It's real tiny, right? But if we rescale the graph so that each one of these little lines is 1/4, that will make this a little bit easier. We could have gone even more, right? We could have made this 1/4. That would be fine as well. But I'm just going to leave it like this. Because these are all fourths, I made each one of these lines 1/4. So now when I go -1, -1/4, remember this is left 1, down 1/4. So left 1 and then down 1/4 is right there. Then we'll do 0, 0. And then we'll do our last one, 1, 1/4. There's our 3 points. Remember, we're going to connect them with a straight line. And then because we want that line to keep going, don't forget to put arrows on the end. Just like that. Now, this does look a lot like that graph we just had on Desmos. Once again, you can see that it's going over more than it's going up with this. And if you wanted to, you can zoom in and so that it rescales it so that it has the same scale as ours, but we don't have to. The graph's going to look the same pretty much no matter what. Okay. The only difference here is the color, which we could change that if we wanted to. I don't feel like it. There we go. Our next graph has another line, and this time they don't give us any x values to pick. So that means we can pick all of the x values that we want. Now I am going to give you a hint on something, or at least just some advice. I shouldn't say it's a hint, but some advice would be, just like last time when we rescaled our graph based on the denominators, we should choose our x values based on the denominators. Because this denominator is a 5, I'm going to choose numbers like 10, 5, 0, maybe even -5 and -10. I would pick numbers that are multiples of my denominator. That's just going to make this come out a whole lot nicer. You don't have to, just some advice. The other thing I'm going to do is look at this on Desmos first, get an idea, make sure we're doing it right. So I'll come here to Desmos and I'll type in y equals 2 divided by 5, and I got to hit over, x, oops, and then -1. I think that's what the equation was. This does give me a pretty good look of what, let's double check and make sure that is right. 2/5 x minus 1. This gives me a good idea what it looks like. Again, I can see the slope of it, and I can also see this point right here at 0, -1. That looks to be a pretty nice point. Okay, and then I can zoom out a little bit if I want to see some other points. There's all kind of stuff that we can check out here for some of these values. But I get an idea of what the line looks like. Now I'll pick my numbers. Let's start out by plugging in 10 in for x. So 2/5 times 10 minus 1. Well, 2 times 10, if you're not sure about multiplying fractions, you can just multiply the tops. So 2 times 10 is 20, divided by 5 is 4. So this gets me 4 minus 1 will give me 3. So I have the ordered pair 10, 3. I'll also put in 5 for x. And then when I multiply 2/5 times 5, actually the 5's cancel out. Like you could think of it as 2 times 5 is 10, divided by 5 is 2. But this 5 and that 5 will also reduce because they're common factors. So anyways, this does become 2 minus 1, or in other words, 1. So 5, 1. 0 is always a nice one to put in because I like multiplying by 0. So y equals 2/5 times 0, that's 0 minus 1, that's just -1. Now we've done more points than we need because we actually only need 2 points to make a line. But you could keep going with this if you wanted. These are enough points though, I think, for us. So we'll plot 10, 3. Remember that's over 10 and then up 3. That's right here. And then we'll also plot 5, 1. So over 5, 1, 2, 3, 4, 5, and up 1 is right there. You actually only need 2 points. But while I can see, I could kind of make a rough sketch of this, be like, oh, this graph, oh, I did not hit that point very well. It's going to look something like that. I can put a few more points on to make my line a little more accurate. So I think what I'm going to do is I'd like to get a point somewhere over here. I am going to take -10 and substitute that in for this value. Even though you only need 2 points, just to make this look a little nicer, I'm going to pick some points that are on opposite sides of the graph. Now I have 2 times -10. Remember, you can take any number, put it over 1. 2 times -10 is -20 over 5 is -4. And then -1 makes this to be y equals -5. So this is the ordered pair -10, -5. When we plot that, you can see that that is right in line with where we thought our line would be. There we go. And you can see that that just makes it a little bit easier to make a nice, accurate line when you have points that are kind of on opposite sides. You don't have to, but it does just make things a little easier. Of course, we do want this to be a line, so I'm going to put little arrows on the end of this just to indicate that we want it to keep going forever and ever. And of course, we'll double check that with Desmos and see that, yeah, I do remember. That's about what that looked like. I have a couple nice points on here. This is the point 0, -1. Here we go. So 0, -1. I also have this point, -5, -3. Here was the one we graphed, -10, -5. So that was a point that we had on here, -10, -5. All right, looks pretty good. These last 2 graphs are a little bit funny. They're actually super easy, but many students struggle with them and get them mixed around. So this is it's an equation in the form of y equals a, where a is a constant. So like y equals 2, y equals 8. Y equals 12, whatever it may be. In this case, it's y equals 1. So it doesn't matter what value of x you pick. I usually like to pick some negatives and some positives. So why don't I pick 5? I don't know, I just picked it just because I like it. So when x is 5, it says y equals 1. Cool. Let's pick another number for x. How about 8? When x is 8, then well, it says y is 1. Okay, well, what about if I pick a number like a negative? What if I pick like -7? You know what? Y is 1. Y is 1 for any of these. So when we go to plot these points here, 5, 1, 1, 2, 3, 4, 5, 1, that's right there. 8, 1, let's see, 5, 6, 7, 8, 1. That's right there. -7, 1. 1, 2, 3, 4, 5, 6, 7, 1. That's right here. I can see that they're all going to be on this nice horizontal line. And so I'll just connect those dots like this. There we go. And we'll put little arrows on the end because we want it to keep going forever and ever. And then that is the line y equals 1. That's because it does not matter what x is. Every single ordered pair on here has a y value of 1. This ordered pair, it's -7, 1. This one is 5, 1, 8, 1. Everything, including all the decimals, right? And of course, we always like to check Desmos just because it's a good idea. And when we come back here and we graph just y equals 1, there it is. It's a nice horizontal line. Now, one thing I want you to think about is what happens if we change this from y value of 1 to, I don't know, maybe a y value of 2. By the way, you can look along here and you can see every point. No matter where I go, that x value keeps changing, but that y is 1. What's going to happen if I change this from y equals 1 to y equals 2? Think about that. Oh, there it is. The whole line is just up at 2. Or what if I make it 3? Or if I make it -2, can you think about what it will look like if it's -2? So -2. There it is. In fact, this is a horizontal line. All the y values on here now are at -2. I was just making up some numbers, right? But every single y value is -2 no matter what the x is. And you can see that Desmos actually allows you to play with some of these, and you can kind of mess around with it. It's a pretty neat, slick little program. All right, so that's a horizontal line. Of course, if we're going to do a horizontal line, we should also probably talk about a vertical line, right? Vertical lines are in the form of x equals a, where x could be some constant, and then y can be anything. Notice it says let x equal -6. That means every single one of these is -6. It does not matter what you pick for y. When y is 0, guess what? X is -6, right? I would come over here, so -1, 2, 3, 4, 5, 6, and y is 0. That's right there. When y is 5, well, it says x is -6. So -6 and then up 5 right there. What about if y was like -10, right? Well, x is -6. It's a constant. So it's back 6 and then down 10 to right there. Of course, this is a vertical line. And if you're doing this on paper, you probably want to use a straight edge. Right? Credit card, student ID, anything like that always makes it look nice. We put arrows on the end of it to keep it going forever. And there we go. This is the line x equals -6. This is a relationship between x and y where x will always be -6 and y can be anything. One last time, let's check Desmos and see what it says. So the cool part about Desmos is it does allow you to graph x equals. Most calculators don't allow you to graph in the form x equals, but Desmos does. And of course, we can see that every single value on here has an x value of -6, no matter what the y value is. And yeah, this looks a lot like the graph that we just made right here. So I think we're good. Now, all that to say, if we come back up here to our start, we could actually plot these. I know it's been a while. You probably forgot about this. But if we look at Lamar's son's height and weight and we start plotting these points a little bit, this was my guess that it was going to look something like that, right? But now let's do this. Okay, the graphs are scaled. They're scaled by tens. I went ahead and put labels on them. It says height is x. That's why I wrote height here. It says weight is y's. That's why I wrote weight there. And we can plot 20, 15. So over 20 and up 15. Well, 15 is going to be right between 10 and 20. How about the next one, 25, 25? So it's over 25 and then up 25. So that would be like right in here. There we go. 35, 35, over 35, and up 35. Looks like it would be right in there. And lastly, we have 40, 45. So over 40 and up 45. Looks something about like that. Now, this is real data, and that's why one straight line doesn't necessarily seem to hit this. Like it looks like one straight line wouldn't quite get all that, and that's okay. The point of this was to be able to plot our points and know that the first number is the x, that's your left, right, and the second number is the y, that's your up and down. I hope this helps with learning to graph, and hopefully you can go back through and be able to graph linear equations by plotting points, horizontal and vertical lines, understand that this is called a rectangular coordinate system. So I hope that helps.